Hello everyone, we are from group 2 and our topic is application of multivariate calculus in conic section. First of all, I'm going to introduce our group members. Our first group members is Janice Lim Ji 277059, second Teh Wei Seng 278131, third Kivenia Priya, daughter of Sandra Sigaran 272972, and Muhammad Fitri Hakim bin Azhar 280046.
Hi, I'm Kivenia Priya. My matrix number is 272972. So I'm going to present the introduction. So firstly is, let's look at the background. Conic sections have been researched and regarded as a fundamental mathematical notion. Apollonius used geometry to write an 8-volume dissertation on conic sections. All three conics were initially explained in the Apollonius theory by using the right or oblique slices of a circular cone. Apollonius also coined the terms as ellipse, parabola, and hyperbola. If you guys look at the figure, you guys can see the parabola, ellipse, and hyperbola. At the absolute least, each conic segment has a focus and a directrix. In contrast to that, ellipse and hyperbolas, which have two of each, parabolas only have one focus and one directrix. Hyperbolas have conic sections that are perpendicular to the axis of rotation. The conic section is a parabola if the plane is perpendicular to the generating line. Conic sections are always secular if the plane is parallel to the axis of revolution. Ellipse is the conic section where the plane contacts one nab at an angle to the axis different than 90 degrees. Next, the key concept. We have two key concepts. First is ellipse and second is parabola. So what is an ellipse? An ellipse is one of the conic sections formed from the intersection between an inclined plane with a cone. In mathematics, an ellipse is a curve surrounding two focal points such that for every point on the curve, the sum of two distance to the two focal points is constant. Ellipses are commonly used in physics, astronomy, and engineering. For instance, the whispering gallery applies the nature of ellipse, such that when whispers at the focal point of an elliptical room, the whisper can be heard at the other focal point. This is because of the reflective properties of an ellipse and its focal points. When the sound is produced at one focal point towards any direction, however, because of the curve of the vertex and the room's elliptical shape, the sound waves reach the opposite end of the room and bounces off of the wall back together into the other focal point. Therefore, this is how the whispering gallery works. On the other hand, what is parabola? A parabola is a conic section formed when an inclined plane intersects a cone at an angle parallel to the cone. In mathematics, a parabola is a curve between a directrix and a focal point such that all points on the curve are equidistant from the focal point and directrix. For example, you can see the usage of parabola in the suspension bridges. When the structure is being built and the main cables are attached to the towers, the curve is the catenary. The cable of a suspension bridge is under tension from holding up the bridge. Therefore, the cables of a suspension bridge is the parabola, because the weight of the deck is equally distributed to the curve. Parabola is being used in suspension bridges is because the bridge deck or a roadway is supported from above, losing tension in the cables and compression in the towers rather than just from the bases. Suspension bridges are also less rigid so they can better withstand outside forces such as earthquakes. Suspension bridges are useful because they can quite long and still work effectively. When constructing a bridge, architects must consider the compression and the tension forces that the bridge is going to have to withstand the compression and the tension. Proceed to the next part is objectives. We have 4 objectives. Firstly is to determine the application of ellipse in the whispering gallery. Second is to assess the application of parabola in the architecture of bridges. Third, to study the nature of ellipse and the parabola. Fourth is to solve the problems related to the applications using the general equations of ellipse and parabola. Next is the methodology. Methodology can be divided into 2. One is qualitative method and another one is quantitative method. What is a qualitative method? Qualitative method is the main method of collecting information regarding the applications of the parabola and the ellipse, where was through literature review, including browsing through websites, YouTube videos, and published research papers. Proceed with the quantitative methods. We have ellipse and parabola. In ellipse, the general equation of ellipse was used in solving problems related to the application of ellipse. There are 2 types of ellipse, namely horizontal and vertical ellipse. If you guys look at the equations in the right, these are the horizontal ellipse equations being used. Next, let's look at the parabola. The general equation of parabola was used in solving problems related to the application of parabola. Same as ellipse, this parabola also have 2 types of parabola. Based on the figure on your right, we used the vertical parabolas. You guys can see the general equation of the vertical parabola is here, where the vertex of the parabola is at xv, yv. If p is more than 0, the vertical parabola has its opening facing upwards. like this. If P is less than 0, the vertical parabola has its own opening facing downwards, like this. That's all from me, thank you. I'll pass to the next presenter.
Hi, Doctor. My name is Janice Lindsay and my metric number is 277059. Today I'm going to talk about the application of ellipse, that is whispering gallery. Whispering gallery is an interesting phenomenon of math and physics. It involves any conic such as hemispherical, circular, elliptical, and more. At the same time, whispering gallery allows a whisper communicate from any part of the internal side of the circumference to any other part. This is because of the refractive properties of an ellipse and its focal points. First of all, there are 2 points in an ellipse which are called foci. For instance, there are 2 people standing on the 2 foci in the whispering gallery. When person A is speaking, person B will hear it at the same time and wait, due to the shape of the ellipse and acting on sound waves emitted from its foci. In fact, the sound waves travel at a constant speed. It hits the wall or ceiling and refers off of it at the same angle in relation to the wall or ceiling when the sound is produced in any direction on a focal point. So, even if you're just whispering on the focal point, the people who stand on the other focal point can still hear it clearly. Next, let me talk about the problem statement of the whispering chamber. A whispering chamber in Washington, D.C. has dimensions that 46 feet wide by 96 feet long. For question A, we want to find the standard form of the equation of the ellipse represent the outline of the room, and assume it is a horizontal ellipse and the central point of the room is at origin. For question B, we want to find the distance between the 2 senators who are standing at the foci of this room. Okay, so let's discuss the solution. Question A. From the problem statement, we know that the length and the width of this room is 96 feet and 46 feet respectively. We let the 96 feet represent the major axis, which is 2A, and 46 feet represent the minor axis, which is 2B. Then we assume the center of this room is at origin. So the equation of the ellipse is x over s squared plus y over b squared is equal to 1, where a is greater than b. To solve for a, we let 2a is equal to 96. Then we can find that a is equal to 48. Then s squared is equal to 2304. To solve b, we let 2b is equal to 46. After that, we found b is equal to 23 and b squared is 529. After the calculation, we can substitute the value of a and b into the equation of ellipse. Therefore, we can find that the standard form of equation of ellipse is x over 2304 plus y over 529 is equal to 1. For question B is to find the distance between the 2 senators who are standing at the foci of this room. So, we need to find the foci first, which coordinates are s is equal to plus or minus c when y is equal to 0. For solving c, we have s squared is equal to b squared plus c squared, and we let the c squared is equal to s squared minus b squared. Then, we can substitute using the value of a and b found in part A, where a squared is equal to 2304, where b squared is equal to 529. Then we can find that c is equal to plus or minus 42. So, the coordinate of foci are negative 42 and positive 42 at x-axis when y is equal to 0. After that, we substitute the value we found just now into the equation of distance. Finally, we can get the distance of 2 senators is 84 feet in this whispering chamber. So, that's all for me. Thank you.
Hello everyone, my name is Dawei Singh and I will be showing you the application of parabola in bridge architecture. Generally, the problems that we face in bridge architecture include stability as well as the cost of constructions. A bridge, especially a long-span bridge, is constantly exposed to high-speed wind as well as the weights of the vehicles driving on top of it. Therefore, a bridge must be built to have a very high maximum capacity and resistance to the wind. As for the cost of constructions, the best desired result is to achieve maximum stability with minimal materials. In order to solve these problems, we can apply parabola in bridge architecture, for example in the Parabolic Arch bridge and the suspension bridge. Before going into the arch bridge, let me introduce to you a little bit about the arch. An arch is a vertical curved structure that spans an elevated space, and it may or may not support the weight above it. When an arch is at rest, there exists a thrust line, where the thrust line is the path of the resultant of compressive force. When weight is uniformly applied to an arch, the thrust line will follow a parabolic profile. However, when additional weight is added onto an arch, the thrust line will shift a little according to the position of the extra weight. If the thrust line falls outside of the arch, then the arch will crumble as shown in the diagram. The parabolic arch is the most efficient among other arches. As shown in the diagram, the parabolic arch minimizes the material usage and contains the thrust line at the same time. The principle employed by a parabolic arch bridge is that the weight on top of an arch is the same as the weight hanging from it. Instead of applying weight onto the arch, the weight is hanging from the arch. In this case, the weight is contributed by the deck as well as the vehicles driving on top of the deck. Examples of the parabolic arch bridge in real world include the Juscelino-Kubitschek bridge. A suspension bridge is thus the inverted version of an arch bridge. The essential structure of a suspension bridge includes the two towers, suspenders or hangers, a main girder or deck, and two anchorages. Vertical suspenders, also called hangers, connect the deck to the main cable, while the main cables connect the towers to the anchorages. How does a suspension bridge work? Weights of the bridge itself and vehicles passing through the bridge exert the compressive force on the bridge. Cables then transfer the compressive force to the towers, which in turn transfer the force to anchorages and directly to the ground. This system has two types of forces, the compressive force and tension force. Both forces work together and give the cable a parabolic shape. One of the examples of a suspension bridge is the Akashi Kaikyo bridge. The bridge is said to withstand an earthquake of magnitude 8.5 and a wind speed of up to 286 km per hour. Benefits of applying parabola in bridge architecture include cost, stability, and aesthetic. In terms of cost, parabolic bridge is relatively economical to be constructed. It needs just a minimum amount of supplies to be built. In terms of stability, tension is most efficiently distributed along a parabola. In terms of aesthetic, the parabolic bridge is aesthetically pleasing and elegant and can be a tourist spot to generate income for the country.
In conclusion, the reflective property of the ellipse at focal points cause the whispering gallery phenomenon. Sound waves around the gallery when a person whispers, clinging to the walls. Sound waves hit the wall or ceiling and reflect off at the same angle in relation to the wall or ceiling. The whispering gallery also appears in nature, such as at South Australia's Barossa Reservoir. These sound waves found diverse applications in astronomy, non-destructive testing, sensing, and even cooling. Meanwhile, the parabolic structure of a suspension bridge and arch bridge gives them many advantages over other bridges. One of the most significant advantages is that the parabolic structures allows the suspension bridge and arch bridge to span a long distance due to the stability the parabola provides. Furthermore, the parabolic structure allows the arch bridge to be built under minimal materials, at the same time guarantees stability. There are several famous suspension bridges and arch bridge around the world, such as the Akashi Kaikyo bridge in Japan and Juscelino-Kubitschek bridge in Brazil. The Akashi Kaikyo bridge is even said to withstand an earthquake of magnitude of 8.5.
Thank you.